Welcome, folks, to another one of our virtual tours of outer space. My name is Josh, and I am so excited to be broadcasting out to you from my home to yours or wherever you're connecting from. We are here to do a virtual tour of outer space, but outer space is big. Outer space is really big, and we've got an awful lot of outer space built into our OpenSpace software. So if there's something in outer space you would like to see, just let me know what sounds interesting to you. Drop it in the comments on our page. My producer Mary's watching, and if she sees something we should target, she'll throw it up on the screen. I would be happy to follow whatever directions you might have to go see some really cool stuff. So as I mentioned, we are checking out our OpenSpace software. I think you can see it right here. And that is actually Planetarium software, but a really cool thing. It's Planetarium software that you can use on your home computer or any computer you have access to that operates, I think it's Windows primarily. But if you have a machine running that software, or I should say that operating system, and you want to check out this software, by all means, please do. You can check it out from the OpenSpaceProject.com. Now, we are using OpenSpace to check out a compelling world in our own solar system. This is, of course, Pluto. Now, I always like to start us off someplace a little interesting, a little exciting. Jessica nailed it if you were guessing what object we were looking at. This is Pluto. Pluto is super cool. Before the show started, Mary and I were talking about our relatively chilly days here in San Francisco. But I got to say, any Plutonian would be making a lot of fun of us. In San Francisco, it's a little cold, it's a little wet, it's a little blowy. But that would be pretty alien to a Plutonian, somebody who lived on Pluto. Not that we think there are too many people hanging out on Pluto. But we are seeing a liquid on the surface of Pluto right here. But this is actually what we are breathing in right now. Take a minute and think about that. Our air would be at such an incredibly low temperature on Pluto, it would puddle on the surface. Now, I called this a liquid. That's only semi-true because I think this is described as a semi-liquid. It is some smushy toothpaste consistency stuff, basically a nitrogen glacier, a glacial lake, you could say, on the surface of Pluto. You can actually see these giant convection cells where something is rising up, kind of like a pot of boiling water, pushing stuff out of the way, and cooler stuff is sinking down. So this is sort of boiling, we think, possibly some kind of energy source under the surface. But if there is something, I think it's pretty mysterious still. I don't think there's a concrete answer of exactly what's powering these convection cells. You can actually see some sort of snowdrifts on the surface too. I would say that's supporting the argument that these aren't completely liquid. They do seem to have some texture on the surface, maybe some goopier, thicker stuff. And over here you can see the amazing mountains of Pluto. Check this out. Now, these don't look like mountains here on Earth because they are formed in a pretty different way. On Earth, our big mountains form when rock bumps into each other on the moving crust of our planet. When it does, it can form peaks. On Pluto, we think some of these mountains are actually being sculpted by the sun through a process called sublimation. Now, sublimation is when a solid goes straight into a gas form. And when that happens, it sculpts some very interesting shapes. If you check out the penitents or the dragon's teeth little ice spikes on the surface of Earth at very high elevation, like Kilimanjaro, the Andes, I think the Himalayas as well, then you get a little bit of the sense of what I'm talking about. Some very strange shapes come from this interesting process. So we are zooming away from Pluto and its companion there, Charon. I've tried to avoid the P word when we're talking about Pluto because I constantly mess it up. Not Pluto, I should say. There are multiple P words. Planet. Now, we set off a firestorm in the comments whenever I call Pluto a planet because on previous broadcasts I've said Pluto's a dwarf planet and that I think dwarf planets should maybe be considered akin to our major planets. But I think the best word I could use to describe Pluto really is world. It is a world around our sun, a place that human beings could go visit. We could hang out on it. It'd be pretty chilly, but it does have a solid surface. An astronaut with a sufficiently robust spacesuit, granted much beyond our current spacesuits, might be able to walk around on the surface and check it out. But whatever category I apply to Pluto, I would argue could apply to Charon, its major moon, as well, because, well, they're similar. They're around the same size. In fact, from this angle, they look almost the same size. But from another angle, Pluto is bigger than Charon, but not a whole lot bigger. You can see that they have kind of a similar color. Pluto tends towards a little bit more pinkish. Charon is a little bit darker, a little grayer, blacker. But when we talk about these two objects, they are very much peas in a pod. Now, because Pluto orbits Charon, you heard that right, and Charon orbits Pluto, I think a very good argument could be made that these are binary worlds. They are worlds traveling around each other as they travel around the sun, and that's a challenging thing for our definition of planet. Turns out a lot of our definitions of planet do not include something orbiting something that's not the sun, and that's a super interesting thing. Natalie wants to know, does Pluto have an atmosphere? It does indeed. If I'd remembered to turn it on before I started the show, we could actually see that atmosphere when we are on the opposite side from the sun. You could see a super cool glowy blue haze around the surface of Pluto, but because I did not enable our atmosphere, it is not appearing. So you can actually see some great shots from the New Horizons mission. As it sailed past Pluto, it was able to catch light bending around the surface of Pluto as the atmosphere caught light from our sun. It's got this light, hazy, bluish quality to it. That's really cool. We think some of that atmosphere is likely the surface getting sublimated, getting turned into a gas and flying off, and that gives it sort of that cloudy effect. We also think that Pluto might change the amount of atmosphere it has based on its distance from the sun. Because Pluto has a very elliptical orbit, I'm going to try and turn our orbit lines on. Boom, boom. There we go. You can actually see this if I get far enough away. When we think about a planet's orbit around the sun, we often think of circles. For most planets, that's pretty accurate. Some of our most eccentric planets, eccentric planets, I should say, are Mercury, has a pretty squished circle for its orbit. Mars also has kind of a squished circle, but neither of them comes close in terms of eccentricity to Pluto. You can see that Pluto is sometimes much closer to the sun and other times much farther away. Now, that change is meaningful, we think. We've only examined Pluto up close at one point in its orbit, basically right where it is right now. We've never examined Pluto when it's very far from the sun, but some people suspect that the amount of atmosphere on Pluto would change based on its distance from the sun. As it gets closer to the sun, it's warmer, there's probably more gases moving around. As it moves farther, it's probably colder, and a lot of those gases contract to the surface. Now, another weird thing about Pluto's orbit you can see right here, check this out. If I line us up just perfectly with the ecliptic, sort of Earth's orbit around the sun, you can see most of the other planets fall very close to our own position. Some might go a little higher, some might go a little lower, but Pluto goes way above the ecliptic and also way below on the other side. Bobby wants to know if Pluto has a molten core or not. I cannot offer any factual information in terms of yay or nay. I don't know if we have a great understanding of the internal structure of Pluto. I would hesitate to guess that if it did have a molten core, it's probably not that active anymore. But I can see Mary might be researching this as we speak, and if there's any information that comes of that, I'm sure she will post it in the comments. But yeah, Pluto is a fascinating world. Oh, one last really cool thing. You can see from Pluto's orbit line, it looks like Pluto is like an olive impaled on a toothpick. Well, that blue line is its orbit as it travels around the sun, and it doesn't stop at Pluto. All of our other planets, it would stop right when it contacts the center of that world. Well, because Pluto and Charon orbit each other, the exact middle of their orbits is right about here, in between the two objects. So that is what we would call the barycenter, or the middle of their orbit. Linda wants to know, where is the closest black hole? I'm not sure of the exact distance. I recall it being somewhere in the hundreds of light years distance. But I will say it's not close. And that fact I can say with extreme confidence. We have no black holes anywhere in our solar system or in the immediate stellar neighborhood that are observable size. There are some theories of quantum physics that say little tiny black holes might be disappearing and reappearing all over the universe all the time, but I'm not counting those. I also don't know if those are completely proven. But if we wanted to get out to the distance where we would expect to see a black hole, I'm actually going to take us out a little farther than hundreds of light years. I'm going to take us to about 1,000 light years. But I would say that there is almost certainly, if we get out to about here, a sun-sized black hole somewhere in the vicinity. Now, when I say sun mass, I shouldn't say sun-sized. So when you're looking out around here, we could expect that at about 1,000 light years distant, there should be a black hole somewhere around there. Now, finding a black hole is always tricky. We need to find them through indirect methods, basically something else getting influenced by the black hole. So seeing the black hole directly is a gigantic challenge. We've recently discovered some fun ways of detecting their gravitational waves on the universe, like the LIGO experiment and subsequent gravitational wave detections. But most of the time, we rely on them moving stars, like the example of the supermassive black hole in the middle of our galaxy. As stars orbit it, they move closer, they move faster. As you get closer to a source of gravitational pull, you move quicker and quicker. That's also kind of what explains Mercury's weird eccentric orbit. It's also one of the fundamental rules of gravity. So as stars get closer to the center of our Milky Way galaxy, they get swung around and shot back out. And we can't see the thing that's moving them, but we can see the stars moving, and that's helped us understand this massive object called Sagittarius A star. Now, Madara wants to know, what is the closest galaxy to our own Milky Way? That's going to be a fun question to answer because it depends entirely on what you call a galaxy. Now, we have little dwarf galaxies orbiting our own. As we pull back, you'll start to see them pop in green. These are all itty-bitty galaxies that are relatively close to our own. Some of them are even gravitationally bound to our own. If you go back to our cosmic conversation with Jackie Faraday, Carolyn Peterson, there was a really cool conversation about the motion of stars around our galaxy. As streams of stars move through, we think they might actually be sort of remnants of previous galaxy mergers. But I do want to answer your question a little bit more accurately. If we want to describe the closest big, full-size galaxy, that is Andromeda. I think Andromeda is at the edge of this representation of the local group. I would guess it's that one right there. So if we wanted to see if Josh is correct, always a fun thing to double check, we're going to dive back into our own galaxy, and we're going to sort of look in that direction. And I'm hoping we will spot the Andromeda galaxy. All we got to do is kind of tilt our heads this way. I've gone completely the wrong direction. Okay, well, we will just find it in the sky. How about that? Okay, there's the plane of our galaxy. We're zooming this way. There's Andromeda, right there. So if you have a very, very dark, wonderfully clear sky, you could probably go out at night and spot Andromeda. It's visible. It's close to circumpolar, I believe. It might be a little bit, it should be pretty high in the sky. But when you're looking for Andromeda, it's going to be tough to see it like this. Mostly what we see is a single blurry-ish blob, and that's really the center of this structure. You can see that sort of a long disk. That's the disk of the galaxy, and the bulge in the middle is really what we see. The actual galaxy is much larger than the object we're seeing, but the only way to really prove that to yourself is by pointing a camera at it and taking a long exposure. When you do that, suddenly all that other fun structure pops out, and you can really see the size of the galaxy on the night sky. And that, to me, is just incredibly cool, that there's a bigger thing there than our eyeballs can reveal. Okay, so will the black holes at the center of the galaxy eventually swallow up all the stuff orbiting it? Very cool question. We think about black holes in science fiction. They're like the drains of the universe, right? Like your bathtub sucks up all the water from your shower. The black hole is going to suck up everything around it. But fundamentally, the tool they would use to suck up stuff would be gravity. And gravity works in a very predictable, understandable way, mostly. Now, we're going to focus specifically on sort of special relativity. General relativity is going to make this argument a whole lot weirder. But for right now, let's just say that Earth is traveling around the sun. We can see its orbit right there. And if I snapped my fingers and turned the sun into a black hole, the sun's not going to become a black hole, but we're doing a hypothetical. What would happen to Earth in its orbit? The answer is nothing. When you change something into a black hole, you're really just making it smaller. You're compacting it together. So if we squished all of the sun down to a teeny tiny area, I think it's like a baseball or smaller, it becomes a black hole. So then Earth would be orbiting the sun. We'd get a lot colder because it would be shining light, but we would stay in about the same position. We wouldn't get pulled in anymore because the mass of the sun wouldn't have changed. We wouldn't fly away because the mass of the sun hadn't changed. So when we look at the size, shape, structure of our galaxy, we can see our sun there. And as I zoom out, we're going to see that our sun is just one sun amongst many. When we look at this, you're going to see all those stars whizzing around us. And at this incredible distance, thousands and thousands of light years distant, they kind of smush together. Part of that's how our software does distance, but also at this distance, it's like trying to spot an individual blade of grass on a field. You can't really. They all sort of just smear together to form light. So this entire disk of our galaxy that's illuminated, the light from that is coming from stars. So I like to say there are hundreds of billions. The number varies every few years, and it depends on what you call a star, but let's say 300 billion stars. So if there are 300 billion stars in our galaxy, the size of that supermassive black hole suddenly seems a little bit more modest. Our supermassive black hole is, I think, around 4 million solar masses. So 4 million times the mass of our sun is big. But the question is, compared to hundreds of billions, it's really not that big. So our sun is flying around the arms of our galaxy, doing our galactic year. I think we actually have an asset for that. I got told last time, oh, you got to use the galactic year asset. So I'm going to try and do that. While I'm poking around, keep checking stuff out. We actually have some really cool measurements of how long it takes our sun to go around. To go all the way around the center of our galaxy once is about 200 million years. That is a super long time. It also is kind of exciting to think that it means that we are still in the same galactic year as when dinosaurs were walking around our planet. That was less than 200 million years ago. In fact, I think dinosaurs began like 2 galactic years ago, which is very interesting to think about. So when we look to the middle of our galaxy, that 400 million solar mass black hole is big. We're not sure if it predates our galaxy or formed right after our galaxy formed. There are arguments for either side, but in either case, we are traveling around it. Because of how we move around it, we're not really getting pulled into it. We're not going to get destroyed. We're in a nice, stable spot around it. If you made the black hole a lot more massive, like thousands of times more massive, then it would have a stronger gravitational influence, and then we might be in trouble. But that's also creating almost a galaxy's worth of stars to just make that thing bigger. And we don't think that's likely to happen. Based on our current understanding of physics, you can't really make a whole lot of matter for free. You also can't get rid of a whole lot of matter for free. It's tough to get rid of. You can convert it into energy, but that doesn't make it free either. Okay, let's see. Where else could we check out? Oh, you can actually see our dwarf galaxies right here. There's the larger and smaller Magellanic Clouds. These are 2 of the little dwarf galaxies that are orbiting around our own galaxy, and some of the most visible ones. You might be wondering, if you say they're the most visible, Josh, why have I seen them? Well, let me tell you, if you live in the southern hemisphere, you probably have. If you live in the northern hemisphere, it's a little tougher. You need to travel below Earth's equator to get a really good view, because these are southern sky objects. Okay. It's always fun to check out the southern sky. From San Francisco, we don't get to see it too often. We just get little slivers. Even big old... Oh, Callisto. Great suggestion. Let's go check out Callisto. So to get to Callisto, I'm going to go in here. I'm going to go to our solar system. I think under planets, we're going to go Jupiter, then moons, and we're going to target Callisto. There we go. So when we're flying into the Jovian system, you can see all these orbits going around Jupiter. That's a lot, but that's really just the Galilean moons. When we show you the Galilean moons, we are actually dropping about 64 moons off Jupiter's count, and it still is a pretty impressive selection. When you look at Callisto, oh man, we came in a cool spot. Check out this impact basin. Now, all those lines are centered on one spot. All of these structures look like shatter structures with something flat in the middle. I am not familiar with the history of this specific object, but I would say that that looks like a massive impact site. But I can't recall in sort of the story of Callisto a giant impact, so I need to go do some research. When you're talking about impacts on Callisto, though, you can see all sorts of them. There are basins upon basins. There are calderas on calderas. There's a ton of action happening here of objects smashing into each other and forming these cool structures. Some of them are very old. We think that Callisto actually records some of the earliest impacts of our solar system and that the surface just hasn't changed that much. Now, that's in direct contrast to some of our other Galilean moons where we have very new surfaces. The surface is constantly changing, repaving itself, growing new material over old, and the history of those objects is disappearing sort of as we speak. They're constantly getting repaved. That is not the case here. So we think the outer shell of Callisto is probably ice. There's a mixture of ice and rock. It's a very cold, very solid object, and an absolutely captivating one. It really doesn't get as much press as the rest of the Galilean family, but I think Callisto is an absolutely fascinating object. Looks like folks are saying it might be Lofen crater, which might be the best name I've ever heard. Just loafing around. But I would want to double check because, I mean, anytime you have a chance to learn more about the moons of our solar system and their structure, it's a cool fact, and it's especially a cool fact if it sticks with you. So in my job at the planetarium, one of my absolute favorite things to do is to tell bad astronomy jokes. I've been collecting them for years and years, and they are great. If you want to remember a joke, the best way to is to tell it to somebody. If you want to remember some of these really cool features on some of these worlds, like Raj's suggestion for Io, I would say the best way for you to really scratch this into your brain and to hold on to some of this information is for you to download the software, play with it, fly around, target one of these worlds, and go look for some of the stuff we talked about. When you're looking at Io, you will see some really cool stuff here too. Very different than our good buddy Callisto. And you might be saying, how different though? Like it's a solid looking surface with craters on it. These are more properly calderas, I should say. But when you talk about these are not impact structures, or at least not most of them, there might be a few sneaking in there, but these are volcanoes. So sort of the opposite of Callisto, where you've got those impacts over time, but nothing much is changing. This is changing. We think there are always volcanoes going off, covering up stuff below. Raj wants to know, is there water there? I would lean towards there being ice there. Granted, there might be some moments where when a lava eruption touches some ice, then what happens? It melts, right? Actually, in this case, no. If you've got something that is not solid ice on the surface, it's likely, and it gets energized, sort of gets heat plugged into it, it's not going to turn to liquid. It's probably just going to evaporate. That's going from your liquid phase briefly into a gas phase where it will escape the surface. So if there is water on the surface of Io, and there might be some water ice, I would say it's probably being depleted over time. Now, we've actually seen some methods that water ice might get returned to Io, because on the next door neighbor moon, Europa, there are cryovolcanoes that blast stuff into space. And if I recall correctly, there's some ideas that support salts from Io ending up on Europa and ice from Europa ending up on Io, which is a super cool, I want to call it interplanetary exchange, but it's really interlunar exchange, which is not a word I've thought of before. Interlunar. That's a good one. Okay, can we see Saturn? I think that's a great idea, Sabata. Let's head to Saturn. Okay, so George asked to see Saturn. Mea culpa, George, let's go see Saturn. Now, when we're flying to Saturn, this is a long trip. From Jupiter to Saturn is probably just a couple months. That's a medium amount of time. From Earth to Saturn, though, our spacecraft took about 7 years to get there. And that is no mean feat. Checking out Saturn, though, you can see these beautiful cloud bands moving around the surface, but their thunder is somewhat stolen by this amazing ring structure. Saturn is a beautiful world. If you had the opportunity to see our cool Jupiter-Saturn conjunction, it's a really special time in our solar system where we got to see two bright, amazing, beautiful objects in the same telescope or binocular view. That was really cool. Speaking of storming, though, you can check out this hexagonal storm on the surface of Saturn, very close to its polar region. That hexagon, that six-sided shape, is real. It's not a failing of our software. That is an actual feature, even though it kind of looks fake. What you're seeing there is a very interesting polar storm structure, pretty different from our polar vortices here on Earth, but still kind of a polar region and the interesting weather they can show. There's a really cool picture of vortices on the pole of Jupiter taken in the infrared, which shows you an awesome set of structures, basically spirally storms in close approximation. And one of my friends pointed out that it really looks like a dish of cinnamon rolls, and I think that sounds amazing. What are all the concentric rings on the surface? Ooh, great question. Ankita, let's check this out. So before I fly away from Saturn, I want to take us to Jupiter next. But let's look at these bands on the surface. And you have this as a great set of structures. These are cloud bands. Basically, if you were able to turn the atmosphere of planet Earth opaque, so our eyes could see it, it wasn't clear to us, we would have similar bands too. On planets, there's a differential rotation. The parts of the planet closest to the equator and the parts of the planet that are northmost actually spin at different speeds. Now, on a gas giant, that means the surface is really changing as you go up or down in latitude. That's what scientists like to call crazy bananas. For us here on Earth, our surface is solid, so we kind of rotate all as one. There's not a huge change. But for our winds, you'll get very different patterns, even different directions as you change latitude. So on a gas giant, that leads to some very interesting structures and interplay between the layers. We're going to see the same thing on Jupiter. Now, a question was asked, how do the rings stay on Saturn if they're not touching it? Well, gravity. Gravity holds onto those structures, keeps them bound to it. You could think of the rings as a bunch of itty-bitty moons trapped around Saturn, but like our galaxy's disk, they are so close together, our eyeballs see them as one thing, even though in actuality they're very spread out. There are some wonderful artists' depictions of the rings of Saturn, basically millions and billions of little tiny chunks of ice flying around it. So remember what we saw on Saturn, those really cool bands interplaying? On Jupiter, we can see the same thing, but this is a beautiful Hubble photo of Jupiter. Actually, this might not be the Hubble photo. This might be an older one. But when you look at this thing, look at that like coffee and cream interplay between the lights and darks. You can see where warmer stuff is rising up, cooler stuff is sinking down. This band seems to be traveling this way. This zone seems to be traveling this way. On Jupiter, and I believe on Saturn too, where you see a dark area is a band, a lighter color is a zone, and they kind of go alternating. Band zone, band zone, band zone, band zone. Then you got that great red spot down here that really tends to steal the show. Up here, you can see those polar regions and all the incredible complexity, the string of pearls kind of formations of all these itty-bitty storms traveling around it. When I say itty-bitty, you got to put a little asterisk there. Some of these are probably the size of Earth or Mars. So those are big structures to be sure, just not quite as big as a honking big planet like Jupiter. And with that, I think we are drawing close to the end of our time. So I'm going to take us back to our very own planet Earth, because I always feel a little bad if we never even see Earth on one of these shows. But as I take us back in, I would like to thank all of you for joining us here for our virtual tour of outer space. And thank you so much for your suggestions. This has been a really fun one for me. I got to say, of all the programs we do, this is one of my absolute favorites because of our interactions with you, our audience. So thank you all for tuning in. If you want to check out OpenSpace, check out the OpenSpaceProject.com and take a minute to really appreciate just how wonderful, how big, and how complex our universe truly is. Thank you for joining me, and have a wonderful